We are 4Space from the University of Oviedo in northern Spain, and this is 4, our second-generation rover, designed around a single objective: reliability. 4Space is a multidisciplinary student team focused on autonomous systems and space robotics. Today, our team is composed of 37 students from electronics, mechanics, physics, mathematics, telecommunication, computer science, biotechnology, geology, marketing, and business. Beyond the competition, we work to bring the space sector closer to students through technical workshops, outreach activities, industry collaborations, and media content created by the team. This season, the entire team structure was reorganized around rover subsystems. Every subsystem has its own lead responsible for development, integration, manufacturing, and testing. That means even the smallest component inside the rover has someone directly accountable for it. To maintain consistency across the entire project, the team is coordinated by dedicated leads. Their role is to define common standards, communication protocols, and integration rules across all subsystems while ensuring the schedule is followed. For example, the mechanical lead defines how every CAD file is named using a standardized convention. So there is no file called piece 1 final version, I promise this is the one version 1 okay printed now.stl. We participate in the ERC because it represents something far beyond competition. It gives students the opportunity to work on real engineering problems under real operational conditions. And after our first participation, we knew we wanted more. Not only to compete, but to improve. 2 is the result of everything we learned during our first season. Every redesign started with the same questions. What failed, why, and how do we prevent it from happening again? Starting with the chassis, the core structure is entirely manufactured from aluminum, providing both structural robustness and efficient thermal dissipation. Every subsystem inside the rover was redistributed to improve cable management. We also redesigned the external covers to enhance access to the internal electronics and mechanical components. For propulsion, 2 uses high-torque motors capable of climbing slopes and overcoming obstacles in challenging terrain. Steering is handled through 4 independent motors, enabling omnidirectional movement. The steering control system was refined with a more aggressive PID tuning strategy, reducing wheel deviations caused by impacts against rocks. Each wheel incorporates an independent suspension system, now upgraded with a parallelogram geometry and softer springs. Power is supplied through 2 6S LiPo batteries operating in parallel. All power distribution is managed through a custom-designed PCB, supplying independent regulated voltages to each subsystem while monitoring consumption and protecting against overcurrents or short circuits. The main payloads, the robotic arm, drill, and science, operate from independent battery systems separated from the main rover power bus. This electrical isolation prevents failures or power spikes generated by individual payloads from propagating to the rest of the rover, improving overall robustness and fault tolerance. 2 uses a Jetson as the main computer and a Raspberry Pi acting as a redundant backup system, both running ROS2. The onboard computers communicate with the rover subsystems through an internal Ethernet network connecting cameras and onboard sensors using micro-ROS and OpenIPC. For real-time actuation, all motors communicate through a dedicated CAN network. For navigation, the rover integrates cameras covering all 4 directions. This visual system is complemented by odometry, IMUs, and a high-precision RTK GPS unit. The primary communication channel is a high-speed WiMAX link used for long-range telemetry, video streaming, and rover control. 5G communication module allows the rover to operate directly through mobile networks and expanding flexibility during outdoor testing. LoRa system is also available in case of emergency to transmit low bandwidth telemetry and critical recovery commands. Safety and fault tolerance were key priorities. The rover incorporates a hot swap battery system, allowing continuous operation even if one of the batteries fails or needs to be replaced during the mission. Also, the new micro-ROS and OpenIPC architecture enables that if the main onboard computer fails, data is still reached. And if everything else falters, an emergency stop button mounted on the rover can immediately disable power delivery to all actuators while keeping the onboard computers and communication systems online. To operate the CAS 2, we developed a fully customized ground control station deeply integrated with the entire rover. Versions of 1 or 2 displays are available to combine portability and amount of information.
But Trust 2 is not alone. This season, we also developed a completely new drone called Numero, named after a mythological creature from Asturian culture, said to control the weather. Numero is a 12-inch frame drone, improving stability, payload capacity, and system integration. This new design provides enough space to integrate onboard computing, communications, power systems, and sensors. Numero operates using ERRS communications, while an onboard Raspberry Pi processes video streams and estimates the coordinates of detected probes in real time. In case of an emergency, a dedicated switch on the controller can immediately trigger an autonomous landing sequence. Furthermore, if communication is lost, the drone automatically lands by itself. The robotic arm is the subsystem that underwent the largest redesign this season. The 3 first joints were re-engineered using new high-torque motors with integrated gearboxes, significantly improving load capacity. The belt transmission previously used in joint 2 was also removed. In parallel, the ARM power system was upgraded to operate at 12S battery, allowing the new motors to deliver their full performance and improving overall efficiency. The drill is able to get samples up to 30 centimeters deep. The structure was reduced and optimized, while the vertical movement mechanism now uses a single motor, eliminating synchronization issues. The sample storage tube was also integrated directly into the drill bit assembly, permitting simultaneous rotation with it during operations.
Last year, the science team focused its efforts on a Raman spectrometer. However, this approach hindered the mission due to its inherent limitation in reliability and precision. For this year's iteration, we have maintained our goal of performing regular analysis while expanding the mission objectives towards the search for one of Mars' greatest questions, the potential existence of life. To achieve this, we have developed 2 complementary experiments based on reflectometry and bioluminescence. The proposed mission area is located in Hellas Planetary, one of the largest impact basins on Mars. Its geological diversity and historical relevance make it an ideal location for studying past environmental conditions and searching for potential biosignatures. This combination of sampling, in situ analysis, and remote scientific operations aims to simulate the type of fieldwork required for future planetary exploration missions.
Last year, we arrived with our first rover. This year, we returned with everything we learned from it. Every failure became a redesign, every test became an improvement, and every student became part of something bigger than a competition. From Asturias to Hellas Planatia. See you at ERC. 4Space and beyond.